Hi everybody, so my name is Nicholas Lane. Today I'll be speaking to you about how we can accelerate GPUs within the context of processing mobile audio. So the motivation of this work is looking at how to increase the utilization of GPUs within processing sometimes continuous or non-continuous examples of sensing from the audio stream. And the motivation for this is because audio itself is a very powerful modality. Many of us in this room use it constantly for building things like mobile health, to assessing stress, using it in terms of digital systems, using it in Amazon's Alexa or on Siri. The question we've got to ask ourselves here is, because these audio sensing workloads are so ubiquitous and so compelling, it's strange that GPUs are yet to be used extensively processing this data. The question is why? And the answer is it's extremely hard to optimize these types of workloads for GPUs. GPUs excel at processing data continuously and in terms of large parallel batches. A lot of work to be done on how you can use GPUs, for example, to accelerate things like networking, to accelerate things like image processing. But when it comes time to look at the variety of signal processing and audio-based models that use in audio sensing, people have really studied how you can use the processor for these tasks. So what you can do in this talk is an approach whereby we can do automated optimization of the GPU for specifically audio sensing workloads. You'll hear that once we're able to accelerate the use of the GPU in terms of the efficiency and latency and energy, it starts to have interesting implications for how you can decide to deploy audio and whether you're going to use, for example, cloud offloading or not. And finally, there's an interesting example here of doing optimization on mobile machine learning workloads where you're not interested in just doing, for example, coarse squeezing of the models down to things based on things like how large the model is, or doing things like minorization. What we're looking at here is how can you map these mobile models to a specific type of architecture. Okay, so this in a nutshell is a technique. On the left-hand side, you see the three phases that we're using to automate the decomposition of the audio workload. You can provide access to any type of audio sensing. It can be speaker recognition, a keyword recognition, or motion recognition. What we do is decompose it into a series of signal processing and machine learning blocks. These blocks are then analyzed by two key components of the system. The first of all is what we call audio GPU packets. And what we did is study the common best practices for how you're going to parallelize and manage the memory constraints that exist within the GPUs, and then map those to the different types of audio processing components that comprise the audio sensing pipelines. These are assessed against what we call packing criteria. These are a series of calculations that allow us to assess how, when we're going to use these design packets, how they're going to be parameterized. Not only with respect to the particular audio workload it's looking at, but with respect to the GPU architecture. So, for example, how many cores does it have, what is the memory hierarchy, and so forth. And finally, once they've been applied, the output of it is a GPU specification that we put onto any sort of mobile GPU, and in the case of implementation, we use CL as a way to make this. And there are two key things I want to highlight about this process of automated GPU tuning. First of all, is that we're performing a full stack sort of optimization. We're not only trying to optimize the model itself, but we're going to optimize the feature extraction and other signal processing that occurs before the model occurs, so that we can have a complete end-to-end of acquisition of the audio all the way to the final inference optimized on this processor. And second, you'll find is our technique will find different ways of decomposing and structuring the computation onto the GPU that's specific for each type of audio pipeline in an automated fashion. So if you give it a speech recognition pipeline, it'll decide, and then you give it a particular GPU, it'll decide how it wants to break this down as a way to maximize, for example, latency and energy. If you give a different type of audio pipeline, it might potentially come up with a different type of composition. Now, these patterns essentially balance two needs. One is the need to decide how you're going to partition the various feature extraction and mobile inference stages into smaller chunks that are assigned to the GPU cores, which you're seeing here. And to do that, we iterate through a series of structural patterns. So essentially, in this case, here we've partitioned the different frames that are being processed through the audio. So these frames typically might be 30 milliseconds. And they're being chunked into different kernels, where inside these kernels, the work items are assigned to do the feature extraction and the model inference. There are different ways you can do this chunking. The task of this phase of optimization is to decide which is the chunking that's going to occur that can allow us to maximize the level of parallelism. And to do this, each candidate type of partitioning is assessed in terms of a number of different parameters. So, for example, we determine that by optimizing the number of essentially the association between the thread count and the final output matrix of the total feature extraction and model processing led to, more often than not, higher levels of parallelism. Now, when you're doing this, you have to balance this against memory contention. So the problem is that if simply by looking for the smallest partitioning of the audio processing is not the means of which you can come up with the fastest latency and the best performance, which you have to allow for the fact that when you decide to chunk the different stages of the audio pipeline, it's going to have large implications for when data needs to reside. And depending on how large the data is and where it's going to reside, it can have large implications for local performance. So there's a constant tension between the level of parallelism you're trying to extract and where you're going to place the data. So to balance the level of parallelism, we have a series of design patterns that are designed to try to mitigate these issues of where the data is going to reside and essentially stop stalling as it is being processed. So I'm going to highlight just one of these techniques. You can see that there on the left-hand side. What I'm going to highlight here is pattern. It's applied in this example to a GMM style audio processing. And this is showing you one example. The example of where there's a local shared memory, there's a fixed constraint, and the decision of how you're going to lay out this computation within the chip is going to affect how much you can do in one iteration. So in this example here, we decided to process 3 of these frames at once through just one of the GMM coefficients, and as a result, we're able to output 3 of the final GMM output cells. Now, the idea of this diagram is that you're not complete, you haven't completed your GMM inference until you finish all of these green cells on the right-hand side of the GMM output. Now, you notice here this alternative tiling example, simply by adjusting the number of coefficients and adjusting the number of frames, here we can actually, one iteration, do an additional GMM output cell with the same fixed limit of memory. So this is an example of the types of design patterns that are being iterated through as a means to understand how you're going to maximize the performance of the GPU. So let's get to the results. We evaluated this framework on a Snapdragon 800 SoC. So this is very much the same sort of CPU that's in the SoC that might be in your phone right now. We compared against a number of baselines based on different processors we find in the SoC. So within this particular chip, you're going to find a DSP, a GPU, and a CPU. We compared our performance against single and multi-threaded versions of audio sensing implementations, as well as in terms of cloud performance, assuming different levels of networking performance. The types of workloads we tested were speed codification, keyword spotting, and emotion recognition. But essentially anything that's used for audio sensing is comprised of, for example, filter bank summaries, or PLPs or MobiSys, and then in turn use GMMs and DNNs can be run through our system. So I'm going to present 4 different results that examine key aspects of the system. The first of these is going to look at how, by using this automated tuning process, you can significantly reduce the latency of performing different audio sensing tasks when you perform these using our tuning system on the GPU of this phone. I'm going to highlight here the CPU that we're going to use as our benchmark. So through this table, it's listing different time gains with respect to the execution of the workload on the CPU. Now I'm going to highlight this GMM. So this GMM here is a pipeline that can execute, for example, speaker ID. It's going to listen for 5 seconds and then determine who is the person speaking. You'll note here that in orange, our automated approach to tune the GPU for this particular pipeline is able to lead to 8 times gain in performance with respect to the CPU, which is not a surprise. What may be a surprise is that we have only 3x performance gains on what we call a naive GPU implementation. Now what this is the exact same design patterns being applied to the same workload, but the tuning is not occurring. To show the flexibility of our approach, here's an audio DNN model. This model is performing hot keyword recognition, so what this means is that you can say to the model in Google or in Watch, it's looking for particular keywords for it to wake up on. It's listening in this context for just 1 second, and then you can see that comparing, for example, the 2 GPU versions on the last 2 areas of the column, you'll see that our gains with respect to the CPU are 13x. Whereas a naive implementation on the GPU that's not tuned is around 8x. Now to highlight the fact that we can extract these gains by tuning on a workload-specific basis, I want to show you the parameterization that's going on being found by our optimizer. So here's 2 example parameters using the DNN, and you'll note that these are distinct. So that are the GMM version, right? So there's different pipelines being optimized, different pipelines and different parameterizations of these DNA. And that's where we need to get from. So that's latency. Let me talk about just briefly about energy. What you're seeing here on the y-axis is the amount of energy being consumed to perform these inferences, both for the GMM and the DNN pipeline, with respect to other types of processes available on this SoC. What we're doing here, though, is showing you not just single inferences, but batching these inferences into wider chunks of time. The important trade-off, I'll first highlight the gains that occur from switching from this standard GPU implementation to our auto-tuning version. So you see on the right-hand side of the figures, there's a dramatic drop from naive GPU to our own version. And next, I'm going to show you the trade-off, the tipping point at which you'll find that our tuned GPU version outperforms every other type of chip under this workload. So essentially it's saying that under the GMM example, if you listen for 10 seconds and batch for that period of time, it's more efficient to compute on the GPU than using the other processor available. The same holds for the DNN when the windows are 6 seconds long. Now what might also be interesting is looking at the cloud offloading story. So this is the exact same type of figure. So for easy comparison, again, y-axis is the energy being consumed to do the one single inference, but we're increasing the batch time to find the tipping point when performing GPU-only computation of this optimized setting actually pays off. So you note here that we're comparing doing offloading against really high bandwidth situations running from up to 20 megabits per second. I'm highlighting the tipping point, assuming that we have a 20 megabits per second link to the cloud, forming these 2 same models again. And you'll see that we have, at the trade-off is at 20 seconds and 10 seconds. So if we simply listen for 20 seconds before we do, for example, motion recognition, it turns out better to do it locally. What this figure doesn't show you is that not only are you saving energy, but you're saving massive amounts of execution time. So you might have 20 or 30x improvements of execution time by performing this locally. Okay, so to summarize today, I'll give you an overview of our approach to doing task-specific optimization for a GPU within the context of audio sensing. We've found that you can increase the benefits of GPU acceleration to a great extent. We're performing audio-specific design patterns and chromatizing these with respect to the particular audio we're doing and trying to optimize for. And this has interesting implications for how you might want to decide to realize certain audio sensing tasks with respect to unavailable processes and offloading options. And finally, it's through insights of building this type of system that we think we can start to generalize this beyond just audio, things like image processing, and not just the GPU, but other types of architectures such as DSPs or network accelerators. So with that,